Today I'm going to talk about reliability, analysis of reliability data using non-Gaussian state space, work with, joint with Java and Laura. Basically, the outline is to talk about the reliability structures that we'll be considering. Then I'll show that this general reliability structure is amenable to applications in a variety of models. Then I'll show you there the need for further structure that will be accomplished in our case with a non-Gaussian state space. Then, if there is time, I'll show you some applications and then conclusions. And I think I'm going to have plenty of time because nobody's controlling time. And so the motivation is that there are a number of models that are available for reliability studies that, and here is a list of some of them, that have the characteristic of having some latent states or parameters that are related over stages, and I'll be more specific about them when we get there. And so there is a need, we don't have to, but the model begs for a relationship between these states, these latent states. And the standard approach, due to the more common use of normal evolutions in latent state space models, is to use Gaussian evolution, and which is okay, but usually leads to analytically intractable models. People don't seem to care about these things nowadays, in the days of NCNC and particle filters and all that, but I think it's still useful to get exact results whenever they are possible. And that's what is our aim here, to avoid these problems that frequently occur in the standard application of stochastic relationship between the parameters in these models. So the main contribution here is to provide a unifying structure that allows for exact inference, free from approximations. So, okay, so the goal here is to show that although these models have a fairly large number of parameters, we can make inference about them without any approximation. And the way to do that, this is achieved with a non-Gaussian state space, which allows for exact, to obtain analytically the marginal likelihood. So not only we have an exact result, but we reduce a high-dimensional problem after marginalization into a very, in a low-dimension problem, and sometimes very low-dimensional problem, which allows easy calculations of, exact calculations of parameters. So this is just a recap of what I just said. We have, I will introduce the structure, show examples, propose a state space, to link the states, and you see the need, I hope you see the need for the link between the states, and then draw inference about the parameters of these models. And then, having time, we'll illustrate the approach to real data sets. So here's the reliability structure. For the moment, this means almost nothing because I didn't put it into a standard framework that you may be familiar with or you have heard of. But anyway, let's assume that we have a problem that can be decomposed, whose likelihood can be decomposed into a product term, and each term in the product can be written in this way. Okay? For the moment, I just want you to bear with me that this happens. This may happen, okay, for the moment. Okay? And so there are known quantities, the lambdas, which change over the stages that in this case are running from 1 to capital T. And there are static parameters which are denoted by phi. Okay? And the yi's are the data. And they are just the sufficient statistics. So the data is summarized into these sufficient statistics. Okay? And there are A, B, and C are functions that need to be defined later. But anyway, let's consider this joint structure, okay? Which basically depends on latent states and parameters. Latent states lambda and hyperparameters phi. Okay? So let me show you some examples where this happens. One example is the piecewise exponential model, which basically is the model deriving from the use of piecewise exponential distribution to analyze lifetime data. So in these models, the risk function is taken to be constant within intervals that form a partition of the positive part of the real line. Okay? So it's usual to model reliability data with through the risk function, and one way to go about it is to propose a specific parametric family, and there are hundreds, millions of them that are being proposed by people all over the world, especially in Brazil. And another way is to allow it to be completely unspecified parametrically and allow the data to tell you how it changes and when it changes. Okay? And we have freedom to specify the intervals. It can be fancy and make them random as well. But let's just get the basic. I just wanted to get the basic idea that for those of you who haven't seen this before, that we are just having this, if you like, non-parametric assumption of letting the data decide how it changes over intervals. Okay? If you have this setting, you have a data collection, and you have this setting for a specification of the risk function, then the likelihood, the results out of this assumption, after you observe a sample from this with this structure, is also belongs to that structure that I just showed you. This one, number one, exactly this one, and the functions A, B, and C are written here. Okay. Okay. Now the point is that we have this non-parametric assumption that allows the risk function to go wherever it likes. It may go, but it's reasonable to expect some smoothness between the lambdas. You typically, in many situations, you don't expect the risk to change dramatically as you move through time. So it is expected that the lambdas are related somehow. Okay? This is not part of the likelihood, but I'm just saying that we may need to add another ingredient to the likelihood for our analysis. Another model that you probably have heard of is the proportional hazards model. It's a very famous model proposed by Cox in '72, and is frequently used to model lifetime data where there are covariance presence. And one of the most common specifications for the proportional hazard rate function is a generalization of the one we had before. Just like the one we had before, now the lambdas represent a baseline hazard, is the hazard that we would obtain if the covariates are all set to 0. And then there is the multiplicative effect of the covariates present here. In this case, it's present in a linear fashion, but there's no need for that. In fact, this is a typo. Our structure allows for any multiplicative function of the covariates. Okay? But anyway, this is the most common representation, and I think this is the one that Cox proposed and used for the calculations in his '72 discussion paper. This model also belongs to that structure that I just showed you, and these are the values of the functions A, B, and C. And once again, just like before, it's reasonable to expect the baseline hazard to be smooth. Or if you have a problem where that's not the case, then forget about all I'm saying. But most models have smoothness as a reasonable assumption for the hazards. So again, you would expect some relationship between the lambdas. the baseline should be, in many applications, smooth, doesn't have jumps as we move through time. Another context where this likelihood that I presented you appear, again in the context of lifetime models, is when you have a regression or Weibull regression that is evolving through time. So you are assuming an accelerated testing problem at each stage, and you want to relate the different stages of this accelerating testing procedure, and this could be one possibility of data that also belongs to the structure I just showed, that I presented you previously. And these are the values of functions A, B, and C, and the lambdas here are these parameters, this scale parameter psi to the power nu, which is a parameter that controls the rate of decay of the Weibull distribution. And again, since this is included in a setup where you're analyzing the same kind of data in the different stages, you would expect some relationship between the different stages of this experiment, so the lambdas should be expected to be related. So we can bring this extra information to help the estimation procedure. Another example is software reliability, and the famous model in this software reliability literature. I think it's the first paper that was specifically oriented towards software reliability data analysis. It is the Jelisky-Moranda model, which basically states that, let me explain. So software reliability data analysis is the analysis of how is the process of debugging a program, a code, before you release for sale or for use. And so the YIs are the times between successive detection of bugs. And you expect, let me just explain to you the Jelisky-Moranda model. You would expect that the more bugs you find, the less bugs there are left. So you expect lengthier period before the next detection. And that's basically the assumption behind the Jelisky-Moranda model, which has constant phi, assumes the failure rate is constant, but it's multiplicative, it's multiplied for the distribution of the next failure by the number of bugs left in the code. Okay? This model has been generalized in many different ways, and I think there are many versions of the generalized Jelisky-Moranda model, but one of them, which is our interest here, allows for the number of bugs. Let me put it this way: we can allow this n0, which is the total, presumably fixed total number of bugs present in your data, in your code, to change over time. And this is because of a number of reasons. The most important one is then, as we all know, when you're fixing a bug, you sometimes inadvertently include, hopefully just one, but sometimes a few more bugs. And we need to be able to take care of that, and that's the main motivation for most of the generalizations of the basic Jelisky-Moranda model. Another one is to allow for failure rates to change over time, over stages, and where the stages are characterized by successive detection of bugs. Okay? But anyway, this model still belongs here to the general framework, and once again, you don't expect the number of bugs, number of remaining bugs, to change dramatically as we move to the process of finding goals. So again, you would expect the lambdas to be somehow related. Okay, there is a change in Simple-Walla model for software detection, software reliability detection analysis, which is basically a model belonging to this class, so I won't be talking much about it, only that it is in the same framework that we are talking about. The only difference is that, I don't know why, they didn't bother including the number of previous failures as an exploratory variable, which we would like to. We think it's an important component of software reliability models, and you will see why. Again, the Weibull model that I just described to you can be placed here. The one that I use for accelerated lifetime, that I showed you that is used for accelerated failure time data analysis, and just can be used here with the inclusion of the number of previous failures as covariates. Okay? And again, this model of, as I said before, it's the same model, the Weibull model that I presented to you. So relationship with the successive lambdas is expected. Okay, so I hope to have convinced you of the importance of including a relationship between the successive latent states, which I call lambda. You don't need to do that, but if you don't do that, you're wasting information, you're wasting valuable information that it's reasonably present in the context of your analysis. So, this has been realized, some people have done that, and the usual way to do that is looking at the fact that the latent states lambda are rates, they are positive. So you use an evolution based on normal disturbances applied on the log scale. That's what one would typically do as a first attempt. And that's actually what I did years ago. And that doesn't work. And what I mean by doesn't work, I mean that it doesn't allow for exact calculation. You have to do approximations. Okay? If you're happy with doing approximations, then fine. There's nothing else for you in this talk. But if you think there is a benefit of trying to get exact results, then please stay on. And this is what we did by allowing for this different relationship here, which is not based on an evolution. Look, this is an evolution relating to lambdas, successive lambdas. So there is this evolution imposes a smoothness on the lambda structure, and this evolution is based on the scale of the lambdas is based on beta disturbances. Okay? And YI here is the previously available information up to that stage. Okay? And you can incorporate covariates by linking this mean function to the lambdas through a multiplicative component G. The model is completed with a prior for the first lambda, which can be the lambda before you start analyzing the data, which is lambda 0, because the first lambda that you need in your likelihood is lambda 1, which comes here. The relationship, the amount of smoothness in this evolution is controlled by these WIs, which can be thought of as discount factor, and they can be thought of as a parameter that controls how much information passes through time. Okay? And there are a number of ways you can specify them. They can be related to the amount of time elapsed between the different stages, if you like. Okay? And we do that. And this is the basic results for us, is that for that likelihood, with the superimposition of this evolution, then we are in a state space framework where calculations are exact. You are allowed to make online inference, you can evolve the lambdas, you can obtain the predictive distribution for the data, all in analytic form. No need for approximations. Okay? And by doing that, we have the likelihood for the hyperparameter side. Note that maybe it went a little bit too fast. All these distributions are conditional on phi, the hyperparameter. Okay? So the phi contains the regression coefficients, the discount factor, and the parameters of the observational model, like the mu in the Weibull distribution, the shape parameter of the Weibull distribution. And we have then the likelihood that is exact and is obtained after integration of lambda analytically. Okay? Wrong slide, sorry. Let's move to the next one. Bayesian inference. So we can make Bayesian inference about psi by combining the likelihood we just obtained with the prior. Okay? And this is the prior that you would like to specify. You can specify any prior you like. In this talk, I'll be using vague prior. Vague priors. Okay? But if you don't like them, you can put whatever prior you like. The point is that we can perform inference of psi exactly, and let me explain what I mean by exactly here. What I mean by exactly here is that if phi is low dimensional, then you can do a grid of points, a sufficiently fine grid of points that will give you precision to 10 to the power minus 10 to your calculation. So this is exact for me. This is now exact. And you can do that very easily if phi is low dimensional, as some of the problems I'll present you. If phi is of one dimension that you don't feel comfortable doing this brute force exact calculations, then you can use approximations. But many problems would not need that. So we get rid of MCMC. You can make predictions. There are formulas that allow you for prediction. And now there is something I need to explain to you. That result I showed you allow for inference about lambdas, given the information up to that time. I think there's a typo here. This should be lambda I, not lambda t. So these distributions allow you to obtain inference about lambda for each stage based on information up to that stage. But that's not what we want. We want to make inference about lambda at each state based on all information. And this can be done using this result, which we call Theorem 2, which allows you to bring back information about, so the information from the future is brought back to the current state by this recursive algorithm that is built based on this result about the theorem that allows you to obtain the conditional distribution of lambda of yesterday based on the latest states of today. Okay? And this distribution is important because it gives you what we need, which is the distribution of the lambdas given psi and all the data, not just information up to that stage of time at which you are interested on. So we can obtain an exact sample from this distribution by doing this recursive backwards operation, which is basically, qualitatively, is the same as the FFPS for those who have seen FFPS before. If you haven't, it's just a recursive algorithm that allows you to obtain an exact sample from that distribution. Okay? These are the estimates that you can obtain, compare against results that I previously obtained with that approximation I showed you. We can make inference and we improve our inference. This is based on specific choice of dynamic factors for controlling the evolution of the normal evolution. This is our approach based on inference conditional on the posterior mode for the discount factor here. And this is the approach that one may prefer based on the consideration of all possible values of the discount factors with their associated posterior distribution. I don't have much time to go through the second application. I just, and you can obtain, and this is the result that we obtain in a lazy way. I'm not going to, the paper is not finished, by the way. And this is, so when the paper is finished, you see the exact posterior density, not just approximations based on MCMC, which are not needed in this case. And then we analyze also software reliability data here and use the Weibull. And I just want to show you that to obtain good results, we beat the generalized Jelisky-Moranda model, we beat the chain of simple Walla, which did not include number of previous figures as a covariant. And there are a number of ways of doing that. There's base, there's empirical base. I know talks here don't differentiate much between base and empirical base, but I still think it's important to differentiate. Anyway, and here's the estimate. So let me just wrap up by saying that we have a general structure that is useful for many settings and allows you for obtain exact inference. You may think it's not important because the number of parameters here is just in the region of tens, maybe hundreds, but nowadays people are using models that are very complex, that contain many components. This may be one component inside your very large model, and you may like not to worry about this particular component and be able to draw in exact inference for that component. So this, I think, is still useful for many situations. And as I said, these are models that people use and propose in the literature, and we have a nice way of handling them. That's it. Thank you.